This program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest UCTV programs.
My name is Ashok Gadgil. I'm the Director of Environmental Energy Technologies Division. And it gives me great pleasure to welcome today's distinguished speaker in the Distinguished Lecturer Series, Professor Andrew Hargadon. His first 2 degrees are straight in mechanical engineering design from Stanford, and PhD is also from engineering in Stanford, looking at management of engineering. I think that's what the department is called. He has worked at Apple. He has taught, I think, at Stanford before. You're a fellow of future professor. I don't quite understand what that Sloan Fellowship means, but he was a Sloan Fellow as a future professor at Stanford. And now he is a professor, so Sloan protected right. And I've heard him speak, and it's extraordinary to get insights from somebody who can step back and look at the forest rather than individually, most scientists being stuck in looking at, I guess, individual cells on leaves of trees. So he's the founding director for the Center of Energy Efficiency at UC Davis, which beat out proposals both from Stanford and Berkeley for the big CalSAFE grant. And he's also the founding director of the Child Family Center, I think, for Innovation Institute for Innovation and Entrepreneurship, which I think you continue to direct.
Right.
So without further ado, please, thank you very much.
Thank you, Ashok. So thank you, Ashok, for the invitation. It's wonderful to come here. In fact, I've worked with a number of you in my role at the Energy Efficiency Center. And so it was good to come down here. I feel like we share a common goal of trying to bring the best in science and engineering to bear on environmental challenges. That's certainly something that we focus a lot on at UC Davis. And in both our Energy Efficiency Center and our Institute for Innovation and Entrepreneurship. So what I want to talk about today is one of the research questions that's been guiding my work for the last decade or so. And let me begin with the context in which that question got sparked. So when James Watt developed his steam engine, the steam engine itself had been around for 75 years. Pumping water from coal mines. And in fact, it wouldn't be another 30 years until Watt's design had an impact on the Industrial Revolution. Henry Ford's Model T came about 30 years after the original commercial auto industry got its start. And Edison's light bulb came after roughly 75 years worth of electric lighting, before he and his design had a profound impact on the electric age. So the question that sticks with me with these stories, when you look closer at them, is where do technology revolutions come from? If in fact we remember these people, Watt, Ford, and Edison, and we give them often much more credit for having launched this revolution. And of course we point to the technologies that they provided us. So this is a really important question, I think, for me, because as I mentioned in my abstract, I don't remember a time when calls for innovation have been any louder. In other words, we're looking at the great social challenges, environmental challenges of our day, and everybody from voters to politicians to the folks in office already trying to drive the next technology revolutions and trying to pick which ones will happen, are all calling for more innovation. In fact, it's interesting, but a lot of that pressure is kind of falling on you guys, right? Your budgets have certainly shifted around a lot, and and the pressure to develop the next great technology is enormous. But at the same time, the public and political conceptions about innovation are fairly distorted. And what I want to talk about is one of those distortions. In fact, that distortion has two causes. The first of which is psychological, and I'll mention that first. It's a cause-consequence bias. It's a cognitive bias by which we try and figure out what happened. Pretty much in anything. You know, if anything happens, we try and figure out how it happened, why it happened. And one of the things we do is we attempt to match consequence to cause. In other words, if the consequence was enormous, then the cause must have been enormous, whatever that cause was. Now, there are two kinds of causes. There are general causes, which are the large, long-term, diffuse causes in the world. And then there are inciting causes, particular things that happen that incite, trigger things. And what we tend to do is, when an enormous consequence has happened, we look for the inciting cause and would give it enormous import as well. Best example I can give you, right? When the straw breaks the camel's back, we tend to give enormous weight, literally and sort of cognitively, towards that last straw, and we ignore all of the other straws that came before it. And in fact, that's actually a very useful way of explaining our understanding of innovation. Because in fact, when we look at innovation, what we tend to see is the enormous revolution that happens, and then we look around quickly to see who was standing nearby when that happened, and give that enormous causal weight. So what we end up with is something called the great man theory of innovation. And this is a theory that was first introduced in history to explain the world as nothing more than a series of great men and their impact on it. That got lost pretty quickly in the late 1800s, but it's persisted in the study of innovation and particularly technology revolutions. And what you end up with then is like this list. This was a list from my daughter's elementary school encyclopedia. What we end up with is continually reinforcing in the public's mind the notion that for every great idea, there's a single point in time when a single individual has that idea. And before that, the idea doesn't exist. And after that, the world is never the same. And you end up with this enormous causal weight being placed on a single person and a single idea in a single moment. And how do you think that shapes the way we think about the innovation process? We manage it, we pursue it, we invest in it at not just an individual level, but an organizational level and a political sort of national level. So in fact, the other reason that this is interesting is because there is a dynamic at work. It's a technological dynamic. It's called the long fuse Big Bang. And what that means is that, well, Rudy Dornbush said it best. He's an economist who said, things take longer to happen than you think they will, and then they happen faster than you thought they could. And by that, what I mean is the steam engine, the automobile, the electric light took decades, almost centuries to develop. And then overnight, well, not overnight, but literally within about 10 years, those industries were fixed. And we live today in the very same electric industry that was established literally in the first decade, in which things began to take shape. So when we think about the long fuse, what's interesting in the electrical age, which is, I'll give you a brief history of the electrical age, the modern electric age. What we have is, in 1800, Alessandro Volta gave us the first sort of predictable source of electricity, the battery, the voltaic battery. By the 1808, Humphrey Davy gave us the two kinds of light we would be living with, essentially. Arc lighting and incandescent lighting. You either consume materials in electrodes, and they create a spark, which gives us light, or you heat an element to incandescence, and it gives us light. So that was already well known. That was already demonstrated in 1808. By the 1830s, that was now, people were developing lighting in both of those cases using batteries. Also in the 1830s, you got the telegraph industry, the first electromechanic use of electricity, connect batteries, and move things at a distance. In this case, electromagnets. Create an electromagnet at a distance. You can move a piston and essentially cause action, which gave you the telegraph, which exploded in the 1830s and created an industry which really didn't change for the next 100 years. But also in the 1830s, you began to get the first electromechanical, or the mechanical origins of electricity, the dynamos, the generators. And a Frenchman, Pixii, gave us the first one. But then fairly quickly after that, in the 1840s and 50s, you began to see other dynamos being created. In the 1860s, that industry exploded. The late 1860s, now all of a sudden we had dynamos, a predictable and large source of power. This was, in fact, the Graham dynamo, then the Wallace and Farmer dynamo. And all of these things took place in really 1867 to 1877, the decade before Edison and the electric light. And why did they emerge so quickly? They emerged because the arc light caused a demand for these dynamos. And over that decade, you began immediately to see not just individual arc lighting systems, or arc lights powered by generators, but entire series of arc lights powered. So that by 1877, Brooklyn Bridge was lit by arc lights in series, run by one of these generators. Central Park was lit by arc lighting. Large mansions, large open spaces and factories were called isolated electric systems, were lit by these systems. So this is to give you some context that when Edison decided to work on the electric light in 1878, there were in place arc lights, incandescent bulbs, there were generators, there were thriving businesses running isolated electric systems using generators to produce arc light in various covered spaces. And so the leap to a system using generators to produce incandescent light was not all of that cognitively great. So why is it that we remember Edison? Why is it in all of this that we look at Edison and we wonder, in fact, here's a picture of a Park Avenue being lit by arc lighting at night. Why is it then that we look at the Edison light bulb, and in fact, we look at it daily probably in terms of PowerPoint presentations, clip art, posters on the wall to describe creativity? What gives us that iconic image, that weight? When really, from another argument, you could say that that electric light was nothing more than the straw that broke the camel's back and doesn't really deserve a whole lot more weight than all of the other straws that came before it. So that's what I want to talk about, because essentially when you look at the Edison impact, what you find is that there were 75 years of gradual accumulation of all of the elements that were necessary to make Edison's system of electric lighting. So that by the time he started, all of the elements were there. Then, within a short period, 10 years, between 1882, when he opened his Pearl Street station, and 1892, all of the elements in the structure of the electric industry we know today were set in place. In fact, interestingly, in that decade, almost all of the large organizations that have dominated the electric industry for the last 100 years were established. Siemens, General Electric, Westinghouse, Thomson Houston, which is now Alstom. All of these companies and a wide range of others didn't exist in the 70s, and in the 80s came into play, and by the 1890s, that industry was set, and we live with it today, including the regulatory structure, the electrical grid, and many of the other associated technologies and political arrangements. So that's what I want to talk about today. And one of the things that it tells us when we look at that, if we look closely at the technology at work, is that innovation is really about connecting, not inventing. Now, I know it sounds a little odd to do that, but bear with me here for a second while I talk about it. Here's a comment that Edison made after visiting Wallace's shop, Wallace of the Wallace Farmer generator, dynamo. He said, "In Wallace's shop, I saw for the first time everything in practical operation." This was the dynamo, the wiring, and the bulbs. It was all before me. I saw the thing had not gone so far, but that I had a chance. I saw what had been done had never been made practically useful. The intense light had not been subdivided so that it could be brought into private house. And what he means by that last comment was, he saw an entire electric system, but he saw it being built around arc lighting. It had never been built around the incandescent bulb, which is a smaller light capable not of blinding, but rather of illuminating a room. So here we have from Edison himself the recognition that everything in place was there. He simply needed to put it together in the right way. And that's what he did. Really, if we look at what Edison did, he took the best of existing electric lights. He took the best of dynamos that were out there powering arc lighting systems. He looked at the businesses of the arc lighting systems, how they were run and how much profit they made. He brought those together. He worked with regulators to define the scope of an electric utility that produced incandescent bulbs. He worked with J.P. Morgan and other venture investors to fund this effort. He borrowed from the utility business model of the gas companies. And he built actually franchises rather than electrical systems himself. He built one to power the Pearl Street Station, and then he sold the franchise to others who would power Boston and Cincinnati and Philadelphia and the other places. And then he worked with local investors in each of these areas to fund it. But the point I want to make with all of this is that one of the things that drove Edison was not the invention of any of these new elements in this system, but rather the arrangement, the particular combination of these elements that would make them commercially successful. And it's not that I'm interested in the commercial success so much as the impact that that rearrangement had on the state of the art, on the technology of the day. And in that particular case, it leads me to another recognition that I hadn't had before, which is perhaps we even have the causality backwards. If innovation isn't about inventing but rather connecting, then where does the invention come from? Because we know there is invention. And one of the things that surprised me the most was that a lot of the invention actually followed the revolution rather than led it. And if I give you a couple things, but the first of which is the recognition that the reason this invention follows rather than leads the revolution is because oftentimes there are great ideas out there, we simply don't hear about them because they haven't solved any problems we have yet. But when a revolution takes place, when a particular new arrangement of all of the existing elements comes into being, it is, as Churchill said, not the end and not the beginning of the end, but really the end of the beginning of this episode of innovation. And in this particular case, when Edison identified a commercially viable system for producing electric light and using it in incandescent bulbs around a city block or 4 city blocks in the case of Pearl Street Station, or then entire cities very soon after that, all of the problems began to emerge of how to make this system work. And it was those very clear and very tangible problems that began to drive the innovation process or the invention process by focusing everyone's efforts towards solving particular aspects of the relationship between those elements. Thomas Hughes is a historian that's looked at the early days of the electric industry, said Edison's concepts grew out of his need to find organizing principles that were powerful enough to integrate and give purposeful direction to the diverse factors and components of the electric system. What that meant was, in fact, I believe it's the next, I'll give you a very concrete example. What that meant in particular, for example, was if you were to build an electric lighting system that powered 4 city blocks, Pearl Street Station, or anywhere else this model meant, Edison did all of the economic calculations of the cost required to build it. And what he found fairly quickly was that the conductors, the lines, the copper lines required were actually 1/3 of the entire cost of the project, just the copper alone. And out of that calculation came the realization that the electric lights, the incandescent lights of the day, weren't going to be good enough because they had a low resistance to them. And he needed something that would have a high enough resistance that you wouldn't be burning all of your energy heating the copper lines of the conductors running from the central station out to all of the buildings. So the very problem of the cost of the copper wiring drove him to develop a brand new electric light, one that had a high internal resistance, that would therefore reduce the cost of copper. And if we remember anything for his electric light's novelty, it actually should be this difference, the switch from a low resistance bulb to a high resistance bulb, and a filament that could incandescent at high resistance and thus save on the cost of copper. The other thing that he had to do as a result of that was also to create a new generator by taking all of the existing generators, which had been designed for arc lights, which were a low resistance, and convert them, they were a high resistance because they were run in series, he had to convert that to a low resistance to run the parallel circuit that would be his electricity grid. Now, all of this is to say that most of the invention, well, let me put it in numbers first. To tune his generators to his electric light, he had to reinvent the generator. He didn't have to invent it. He simply had to adapt all of the ones who were out there. And if we look then at what he did, what we find quickly is, in his notebooks, when he founded the Edison Electric Company with this iconic invention of a light bulb, his company submitted and were granted 14 patents for his inventions. When he began building the Pearl Street Station and got to work, so the first 3 years of his company, he was granted 14 patents. In the second 3 years, as he built out the Pearl Street Station, he was granted 368 patents. What this says, actually, very interestingly, is almost all of his invention actually took place when he had to start making the system work. He had to develop a generator that powered the right light bulbs with the right economics associated with it. And then once he had that generator, he had to figure out a way to control it, because if it looped out of the voltage parameters, or if it looped out of the current parameters, all the bulbs would pop. So he had to create new controllers on his generator to make sure that they didn't ever exceed the performance parameters. And then he had to create new bulbs that worked in parallel, and he had to create switches for those bulbs, and then he had to create electric meters in order to measure the electricity consumed in individual houses and offices. And then he had to create insulation for the wires to bury them underground. He had to create an enormous number of inventions simply to make the system work together. All the elements were there, but they hadn't been adapted to each other. And all of his inventive effort actually went into making the system work. But Edison wasn't the only one that began inventing only after he began building. If you look at the electric system, once he had it in place and could prove that there was commercial viability to it, that created a brand new set of demands that didn't exist just a few years before. So what we have here is Charles Parsons' steam turbine. In 1884, after the notion of the electric utility came into place, Charles Parsons built a steam turbine that was capable of producing 7.5 kilowatts of energy. And now, we look at this and think, actually, you may not look at this, but we look at that and think that's, well, you may not anymore look at that. I think that's amazing, because it was at least twice, almost 3 times the size of the existing turbines, the steam engines. But at the same time, 2 years earlier, there was no need for a steam turbine that produced 7.5 kilowatts worth of energy, because there was no system that consumed that much energy. Within the next 10 years, he produced a 1 megawatt steam engine. And again, 10 years earlier, there was no possible demand for such a large system, large solution. Now, all of a sudden, every city in the country demanded one. Within another 10 years, he had a 25 megawatt system. In fact, it went from 7.5 kilowatts at 2% efficiency to 1 megawatt at 5% efficiency to 25 megawatts at 25% efficiency. And the reason for that dramatic improvement wasn't because he sat in a room alone coming up with that, but rather because the market demanded it, and it had never been applied at that scale. At the same time, we have AC. Nikola Tesla and Westinghouse developed the first AC generators. And then almost immediately thereafter, the first AC motors. This happened in 1887, 5 years after Edison opened his Pearl Street Station, and in fact was the single sort of significant change in that decade that overturned Edison's dominance and gave it to Westinghouse and others who adopted the AC dynamo. But you're probably all familiar with the advantages of the AC motor. The AC dynamo and motor, the AC dynamo was more efficient at transmitting electricity at distance. Now, coming back 5 years earlier, everybody had isolated electric systems. Nobody bothered to generate and transmit electricity at distance. It wasn't until Edison proved the utility model of electricity was viable and people began building them that the AC motor had any economic value, displacing the DC motor as a dynamo, as a dynamo, because nobody transmitted at a distance. So you didn't have any of these problems until the system came together. And then you had this flurry of invention as people solved these. And the AC motor, again, was a much more efficient and worked with the AC system. So not to belabor the point, but I think the challenge I want to bring to you is that, in fact, much of the innovation potential is in the connection of existing elements, which, once connected, immediately surfaces a wide range of problems for which inventions become valuable solutions. And just to bring that back to the modern day, one of the things that it tells me is, in fact, when we study innovations, we often tend to look at individual ideas, materials, technologies. What we don't fully appreciate is the network itself is the innovation. The particular arrangement of organizing principles that Edison came up with to create electric utility that was commercially viable. Once that's created, we recognize it as obvious, and we begin to see immediately a new industry structure take shape. So let me give you a modern example of that I think you probably are all very familiar with. The iPod. It came out in 2001 and immediately overturned the MP3 player, really the sort of, does anybody remember the Walkman? Does anybody remember thinking about the Walkman in 2002 or beyond? It went from 30,000 models in every retail environment you could imagine to absent within a period of about a year. And so we can say that the iPod fundamentally overturned the music player market. We can also say that the iPod wasn't the first MP3 player on the market. In fact, we can say that the elements of the iPod were already there in places, and then ultimately, in fact, in about 15 different MP3 players before Apple came out with theirs. So there was no invention there. In fact, when Apple developed their first iPods, they went out and they pieced together existing elements of the other MP3 players that were on the market. They used Portal Player for the chipsets. They went to Pixo Design for their user interface. They bought that company. They brought in their industrial design, but they used Wolfson Microelectronics, Sharp, Sony, Linear Technology, and all of the MP3 licensing formats that they needed to license to build one of their own. So the novelty of the technology doesn't really account for their impact. One of the things that Apple did, though, that was different was that they recognized they had an organizing principle, a set of organizing principles around their system that was better than anybody else's. They could seamlessly tie their MP3 player to the Macintosh operating system and to the iTunes Music Store, which, of course, they didn't also build, they bought. And it was a knockoff, of course, of the Napster interface that was already out there. And then they brought in the electric company. Then they brought in the record labels into the system to make it commercially viable. That was the first opportunity the record companies had, the record labels had, to sell their songs legally online. So they jumped into this system and they made it work. And then the system began to grow, and podcasts and user-generated content, the internet, photographs, television shows, movies, all became part of this system. And then soon after that, they incorporated cell phone circuitry into the iPod. Make no mistake, it didn't go the other way. The iPod or the iPhone is really an iPod with cell phone circuitry inside it. And one of the things they learned with the iPod was that it was a great developer platform. People could use it to develop applications that could run on that new system. And the application environment, in fact, was really a lot of the value of this new network. As Walt Mossberg said, he was one of the Wall Street Journal technology reporters, the iPhone was the first electronic device he had ever owned that got more valuable the longer he used it, because more people would be writing more apps for it that all of a sudden answered the problem, where'd you put your keys? What's your next appointment? Where are you? What do you need to do tomorrow? All of these things were things that you didn't really have an app for yet, and now all of a sudden you could have it. And it became more valuable, not because of any individual technological breakthrough, but rather because many of the things that were already out there in different elements came together in a particular way that gave us this. Now, it gave us this and had an enormous impact, right? We have 350 million iOS devices, iPhones, iPads, Apple TVs out there now that run this. With over 25 billion apps downloaded, we can see how much of a phenomenal and ferocious shift this was from 10 years ago. But we can also see that effectively that industry structure is now in place. if you've been paying any attention to the Apple, Samsung patent lawsuits, what's most interesting to me about that lawsuit was, in fact, that yes, the Android environment almost exactly replicated the iOS environment. Everything from the app stores and the app developers down to the look and feel and the relationship between the operating system, the developers, the retailers, and the cellular carriers. That entire industry structure was not there roughly 7 years ago, and I suspect that it will be here for the next 50 years, because it's a structure that's now put in place that sort of froze overnight as soon as it was introduced. And what you have, again, is now most of the invention is actually being directed towards making the system work so seamlessly and smoothly together, rather than creating new systems. So what I want to finish with is a description of partly why this works so well. And what I want to do now is actually come back to one of the other examples I use, the auto industry, to understand how these impacts can drive revolutions so quickly. And it's not simply that they're put together from existing elements that are out there, but the process of putting together in that way has a profound impact. This is Henry Ford's mass production. The Model T was, again, the car was a 30-year-old technology. What Ford was able to do was move it from a $3,000 product for rich people to a $300 product for the mass market. He introduced his Model T in 1906. In 1907, he began producing it. He produced 1,600 cars that first year. 7 years later, when he had perfected the system of mass production, he produced 265,000 cars a year. In other words, he went from 1,000 cars or 1,500 cars a year to 1,000 cars a day. And he went from $3,000 a car to $300 a car. There were 4 core technologies behind mass production. In many ways, just exactly like the vista that Edison had on the electric industry, Henry Ford could look out and see 4 core technologies as central elements to mass production. Interchangeable parts, the ability to build 4 wheels and have any one of those wheels, or 4,000 wheels, and have any one of those wheels come down the line and go onto any one of those 2,000 axles, onto any one of those 1,000 cars on any given day without worrying about filing anything to fit. It all came together seamlessly. It was continuous flow production. The ability to have barges of iron ore pulling up at one end of the factory, engines cast, engines machined, pistons inserted, engines slapped onto chassis, wheels, et cetera, all coming and moving continuously through the factory. And what was essentially a mass balance equation. I'll be quick on this as we come to an end. The third piece was the assembly line. Ford said, for 8 hours a day, men become part of the machine. The assembly line allowed Ford to put people in the middle of that continuous flow production process and give them each very simple tasks to do and move the work past them. The last piece was the electric motor. The electric motor allowed Ford to decouple the factory system from a central steam engine, the source of power that was originally there, and allowed him to put his machines where they needed to be so that the work could flow continuously, and then simply attach wires to it. In fact, in this picture, you see the remnants of the old factory design in the shafts and wheels and belts hanging from the ceiling, which was how the power from the central steam engine was distributed. But if you're going to reorganize your manufacturing system entirely around mass production, you need to put the machines where they're in the best order of the flow of the work. And that allowed him to do that. Now, what drove that innovation to have such an impact that we remember Ford rather than any of the other automobile inventors or manufacturers? In many ways, it was the very fact that these ideas all existed before. Because had he tried to invent any one of these elements, they could not possibly have scaled from 1,500 cars a year to 1,000 cars a day. And in fact, in the last 3 years of his business, from roughly 25,000 cars a year to 265,000 cars a year. Now, the other reason I think this is so important is we recognize the interchangeable parts was an idea presented to Congress in 1797 as a way to make muskets. By the 1830s, the machine tool industry had evolved. By the 1870s, Bessemer steel and high-quality steel had come into play. So that by the time Ford got to it, he didn't have to develop any of those things. He could simply take the best machine tool designers and salesmen and give them carte blanche to design his factory. Continuous flow production was already happening near Detroit in Chicago as the food products being grown in the Midwest were being canned and shipped, packaged and shipped back east. In fact, when he built his factory, he built it out of catalogs for parts from continuous flow production. The assembly line came from the Swift meatpacking plant in Detroit. As they looked at it, they went back there and they saw how the slaughterhouses of of Chicago were disassembling pigs and cows. Walter Klahn, one of the engineers who designed the assembly line at Ford, came back from that visit and said, if they can kill pigs and cows this way, we can build cars this way. And then finally, the electric motor was already in use in printing and textiles. And the important piece I want to say about this is the dramatic impacts that we look for in technology revolutions don't come from a brand new idea. They come from the connection of all of these existing ideas in new ways. Because when that connection happens, those ideas can immediately contribute. They can immediately begin to change the world. All that's left then is the inventions required to make those pieces fit together as well as possible. And the reason I like that story in particular is because Henry Ford understood that. Behind the Model T, when he was asked who invented it, he said, I invented nothing new. I simply assembled into a car the discoveries of other men behind whom were centuries of work. Had I worked 50 or 10 or even 5 years before, I would have failed. So it is with every new thing. Progress happens when all the factors that make for it are ready, and then it is inevitable. To teach that a comparatively few men are responsible for the greatest forward steps of mankind is the worst sort of nonsense. It's a wonderful bookend to the great man theory in the sense that he understood completely. Now, mass production was just getting started, and it's improved enormously ever since then. But within those first 10 years, the automobile industry was fixed. In the same way that within the decade of the 1880s, the electric industry was fixed. Not because of invention, but it drove invention, because the elements were already there. So I just want to finish then with launching into this set of questions of where then does science come in when much of the invention that's required actually follows the new combinations rather than leads to them. All right, and I want to say thank you. Quick.
Thanks so much, Andy. We have time for questions. I would like some volunteers to make sure that people who ask questions get the mic so everybody can hear what the questions are. The first question.
Yeah, thank you.
Thank you. Thank you. Can you hear me now?
Yep.
Good. Thank you for your talk, Andrew. So looking ahead, and since a number of the people in the audience work on energy efficiency technologies, renewable energy technologies, do we need to wait for that person to come along? Or another way of asking this question, what's the role of government in invention, innovation, and similarly the role of markets and getting the right policies in place?
This is the billion-dollar question. Actually, technically, in the U.S., it's about a $55 billion question, right? How much funding we have for basic research in the country. I think one of the most important things we need to be doing is rethinking the major drivers of innovation. So science clearly provides benefits. But when we begin to think of our investments in science as solving specific problems in specific time frames, that's when we get into trouble. Because there was 75 years of good science developing the battery, electric light, arc lighting, lots of nice explorations, but it wasn't until it became a commercially possible system that we really had the tremendous change that we then now look to and say, climate change, we need a change and we need it now. Where's our science? And it doesn't work that way. So I think part of our challenge is simply to get a better shared understanding of what are the engines of change. And often, to be quite blunt, the market is that engine of change. and you can't go against it. In other words, you can't artificially create a market that isn't there. We're seeing that now with with solar, and the European subsidies are gone, our subsidies under pressure, and is the market going to survive when part of the commercial value of it is no longer there? We're seeing it in cars and energy storage and car batteries. So I think that, I don't mean to be punting on the question, but I think we need to recognize what drives the major challenges, and often those major challenges aren't clearly identified until a commercially viable system becomes accepted. And then immediately, there are very clear sets of problems associated with it. And now everybody's scrambling for a scientific solution to those specific problems. And so it's almost a bit of taking the pressure off of science to lead these revolutions, but putting pressure back onto science to be engaged in the conversations that are happening around emerging systems when they do take off, because that's when the problems are clearly there. There's a historic shift. Up until about between 1930 and 1950 is when there was a slow separation between R&D and manufacturing. And no longer were the R&D professionals housed in the same offices and factories as the manufacturing was. They were put off into office parks, into R&D facilities, and they were no longer connected to the problems of commercial, of manufacture. And that's when, in many cases in organizations, R&D stopped being useful to manufacturing and started being a separate wing devoted towards, in many ways, creating brand new opportunities, which, when we look at AT&T and Kodak and Xerox and others, we find didn't really work out so well. So, finding ways to merge them back together again at the appropriate moments is, I think, going to be critical. Go.
I want to ask if maybe Henry Ford's quote could be used to support the big man theory of science in the following way. At the end of the day, it's Henry Ford who made the money off all those discoveries. And don't we need the big man theory in order to keep those hundreds of other people inventing things so Henry Ford can come along?
Yeah, there's Henry Ford, Thomas Edison, Steve Jobs. These are great, but they're great for different reasons. But I also think we need to bear in mind his claim that, had I tried 50 or 10 or even 5 years before, I couldn't. But then it was inevitable. Once those systems are in place, we can give them credit for being the ones that drove their particular view of the system together. But in many ways, because those existing elements were all out there in the 1870s, for example, with electric lighting, it's possible that system was inevitable anyway. The elements were now there. So we have to, and we give them credit for what they accomplished, but I don't want to place them on too high a pedestal. But I will say that it's important to recognize that the effort at innovation needs to include people who are thinking at the systems level, and people who are capable of going, like Steve Jobs, to the chairman of Universal Vivendi and convincing him that this organizing principle, this relationship, was worth committing to. The ability of Edison to go to JP Morgan and say, this system of electric lighting is worth investing in. Or to the regulators and saying, you should allow me to be treated like a gas utility because this system is viable. There's an enormous role played by those people who make those connections. Yeah.
Despite your downgrade, despite your downgrading of scientists, most of us still find we have to write proposals to innovations, initiative, blah blah blah.
I'm not downgrading. In fact, I'm a professor too, by the way. I make my living by research.
Can you give us something useful to put in our proposal? Specifically, what is your favorite innovations book of the day that the management weenies who are reading our proposals will have written? Will have read. Sorry.
Isn't that scary? That's a rolling. I was talking to Ashok about this. It's a rolling 5-year average, right? We have a new management theory every couple years, and people don't remember beyond the last 5 years. And it's no longer good to call yourself the Google of whatever you're doing, because that's the bloom is off that rose already. No, honestly, I think the best thing can be, and believe, I'm a scientist too. I simply happen to be a social scientist. which means we have no pressure to change the world, right? We're simply observing it. But we still write grant proposals, and our biggest challenge is to industry partners and proof of clear need. But you run the risk, because it's when you have a clear problem to be working on, you have something you can now fall short of. And I can't speak to you, but I can speak to the university culture, which is the last thing we want are to be held accountable for for solving specific problems. And so we have this dilemma of claiming that we're vital to the innovation process because we're solving humanity's problems, but just don't put us on any one of them or hold us to any timetable. Yeah, it's a great gig if you can get it.
I'm concerned about the rollout of new technology and the missteps in design and the mishaps that happen afterward. I think everybody in this room felt like they were beta testing Microsoft software at one point or another. I'm, as an ergonomist, I've been involved in lots of poorly designed equipment, tools, keyboards, etc. So could you comment on this? I have a feeling that some of this goes back to your comments on the separation of R&D and manufacturing historically. But could you comment on how we can do a better job of not putting our customers in the position of beta testing everything we put out?
That's a tough question. One of the things that I found in working with I spent a lot of time with our scientists trying to commercialize their work, and or actually trying to educate them and commercializing their work. And one of the challenges is the difficulty of iterating, of prototyping, of getting a solution in place that others can use that are not PhDs and are not, and that cycle, the iterative cycle, is really the crucial piece of that. The more times we can get through it, the less we're exposing our customer to the beta problem, because we've developed our betas, we've used them, we've shared them, we've improved on them. Oftentimes, what we release at our university, and I think at most universities, is the best thing we could possibly build with the basic research grant that we were given. Not the thing that's best to be used or the best to be manufactured at scale, but rather the best thing that we could do to generate the best scientific results in our experiments. And we leave it to everybody else to try and figure out how to then take that and find something useful to do with it. And it usually ends up being too costly and sort of fragile for its final uses. Yeah.
Hi, up here. I found the first question to be very interesting, and I think your presentation actually offers a slightly another answer to that question.
Yeah.
Which the question was sort of what is the role? There was a question of what is the role of government in all this, and it seems that from your presentation that once the system is put into place, that's going to spark a whole round of innovation, of invention, to solve all the problems that are created by that system being put into place.
Right.
But you note that that system could only be put into place when a whole bunch of other stuff happened first. And that other stuff there wasn't as much of an economic driver for that other stuff because that big system wasn't yet in place. So it's sort of, to me, it sort of, encourages a government investment in the basic science to produce inventions that may not be, the need for those inventions may not yet be clear. So there's an advancement stage that happens before the system is in place. Because once that happens, okay, then there's commercial drivers for all those other inventions that the government doesn't need to be involved with.
Okay, so let me muddy that water. That's a great response, and I appreciate it, because yes, there's absolutely a role for generating new science, new findings, new discoveries. There's also an enormous role for science in explaining old discoveries. So the laws of thermodynamics, were built to explain why steam engines blew up. They didn't invent steam engines; they explained them. And in fact, Hooke's law really was the driver that allowed Watt to understand what was going on with all of the energy being lost in the old Newcomen engines and design his system. So there's an enormous role for science, but it's not. But it shouldn't be placed in. It shouldn't be given responsibility for creating the next revolutions, because that linkage, that causal linkage, isn't there. The other thing you mentioned about science that's really important to recognize is, government, is that government didn't discover penicillin, but it drove the commercial manufacture of it. And I mean, it was one thing to isolate and manufacture small quantities of penicillin in a laboratory, able to test on a dozen mice or 6 people, barely. But when you got to producing millions of units of it a day, that was funded by government as part of the mobilization of World War II. And that was where most of the invention in penicillin took place, was in learning how to build it at scale. Radar existed in the elements already by World War II, but it was government procurement that said, we're going to wire the entire coast of England with radar. And then that system, once that system was built, they provided the impetus, the commercial value for that system. Transistors, the same. The missile industry in the 50s were what drove the development of the transistor industry, the semiconductor industry. So government plays an enormous role, not only in funding the original science that gets things moving, but in actually being the customer of that first system. And I think that's actually where government is sort of falling short on a lot of this energy stuff, is we have, the military has yet to fully embrace the value and say, I want these systems. You want to see advances in microgrids? Wait till the government says, I want microgrids on every plant, and I want, and then then we're going to see immediately the problems we have with them, and we'll start to bring them economically down into the viable range for elsewhere. So the government plays 2 roles. I think we're actually weaker on the procurement role, and government's putting way too much responsibility on the scientists for coming up with the next great transition. You'll get me talking all day. The important thing to remember on that, the advances in dynamos were driven by arc lighting systems. So there was commercial value in developing the dynamos. It was for arc lights. It was, and so there was usually always something else, some intermediate markets that are driving a lot of stuff.
So we have time for 2 more questions respecting the schedule for the talk. But maybe we have a little more informal questions afterwards. One is from Amol there, and second is from somebody there whom I can't see.
Okay, okay,
Yes,
great.
I think really fascinating talk. I think the question about what is the role of the government, right? I think the question is about, it's not about yes and no, it's about scale. Scale in a sense, is the current investments in RD&D need to increase twice or 5 times to address some of the challenges we are facing? And that's where I think having some empirical understanding of a linking between the funding to RD&D, which creates kind of the necessary condition. I mean, that's one way to put it, that it creates a necessary condition for innovation to happen. It's not a sufficient condition, because then you need these connectors to connect it. But that's the question that's going to get asked. Should we fund it at a $100 billion level, or should we fund it at a 500? What's the society's return on RD&D investment? And any kind of insights from your empirical work, or any kind of insights you can draw on, that would be very useful.
To be honest, whether we funded it at 50 billion, 100 billion, 500 billion, it's a matter of where we fund it, how we use those funds. And RD&D is a wide spectrum, of places to put that money. But it's also how we hold it accountable. If we put all of that money into early stage research and we neglect the development, deployment, demonstration, and deployment, then we're spending it badly. But so it needs to be the appropriate balance, is really what I think you're asking for, is how much would you put in each bucket? But I even think that's a dangerous question, because most of the invention that needs to come will come from systems that are emerging, that have already been adopted by the market in some preliminary form, or by government as market in some preliminary form. And so there needs to be even a little bit more strategic investment than that says, these are markets where there is commercial viability. Now, how do we bring the best science to bear on the problems associated with it? How do we, it's tipping the scales, but it's often not tipping the scales with new science research projects that may take 5 or 10 years, but rather with the people who have done the last generation's worth of science, who knows it and who can say, well, have you thought of that this, or there's this material that's out there. There's an odd connection going on that we don't really fully describe or appreciate. It's actually captured in a lot of the explanations, particularly explanations that university chancellors give around science, which is, look at all the great things that we did that led, look at all the great things that were led to by the things that we did, which is all retrospective. It's never prospective in the sense of we knew what we were doing when we did it, and we, it was simply a matter of looking back. We created these things, which really was, So I think we need to recognize a little bit more that you don't control science in that way. So it's dangerous to start investing in science as if you do. You need to treat science in a particularly different way than that. And for most of the part, it has been treated differently. But these days, it's become the driver for change, and we expect it to be different. And I think that's where we get into trouble. We had one last question.
Last formal question, yes.
Yeah.
We have talked a lot about how innovation spurs and emerges new industries, but also you pointed out that new industries can very rapidly, within a decade or two, freeze or multiply. Like the companies starting the electric industry, they are still around, and then how can we as a society structure boundary conditions so that these industries remain vivid and continue to undergo a lot of innovation?
Oh, that's I'm not sure you want that, actually. That's an interesting question. Yeah. I mean, how many years do you want to spend buying a new phone every year?
I do want a new grid once in a while.
Yeah. Well, maybe if you think. But now we're back to the problem of living life in beta. The old grids were not particularly reliable, and so what we got with that mortification of the industry, I think is your term, a wonderful word, is reliability and performance. We're I think 1/400th the cost of illumination right now as we were back then. So we have an enormous benefit from that mortification setting in and the fine tuning and the making efficient of it all. I think one of the challenges we have, though, is now we're back to the government, is our regulatory environment actually needs to be more labile than it is. It's not keeping up with innovation. And so, it's hard enough making something new that's commercially viable, but when it needs to be new, commercially viable, and the regulatory environment needs to adapt to accommodate it, now you're asking not just scientists and entrepreneurs to be involved, but scientists, entrepreneurs, and lobbyists. And science and entrepreneur, you can't afford lobbyists, right? So there's a real challenge here, and we're seeing it in microgrids, we're seeing it in community solar, we're seeing it in fuels that are the regulatory environment. If it doesn't change with the new opportunities and the new then we're still frozen. I think all I did there was add one more variable to the mortification soup, but it's an important one. Okay.
Thank you.
Thank you.
Really
Thank you. Great. Thank you.